In this video, we will look at how to use the calibration block in a mission. A calibration block lets you describe your RF path so you can achieve the best possible measurement accuracy. You can easily add a calibration block in the block graph editor. Either drag and drop the calibration block from the results list or simply double-click it. Now connect the RF output of the calibration block to the RF1 input of the Spectran V6 Eco block. If you want to use a second RF input, you can add another calibration block in the same way. Double-click the calibration block again, then connect its RF output to RF2 on the V6 Eco. Click AutoFit to clean up the layout and remove any crisscrossing connection lines. You can also cascade calibration blocks if you need to model multiple elements in series, such as an antenna followed by an attenuator. Add another calibration block and connect its RF output to the RF input of an existing calibration block. Then run AutoFit again to tidy up the view. Next, click one of the calibration blocks to open its settings on the right side of the screen. In the right panel, you can drag the border to give yourself more space. Click the interlocking gears icon to open the block settings. In the title field, you can give this calibration block a more meaningful name. For example, enter Antenna Only. This makes it easy to see which block describes only the antenna and which blocks contain additional components such as amplifiers or attenuators. You can repeat this for other calibration blocks in your mission so each one has a descriptive title. For the rest of this video, we will focus on the calibration blocks so you can delete any extra blocks that are not needed. To create more space for the main GUI, close the block graph editor at the top. Now locate the calibration section for this mission and expand it. Click the interlocking gears icon there to open all available calibration settings. We already looked at the title. You can also store and recall presets if you want a configuration that you can quickly return to later. Now let's focus on the main settings and the frequency response graph. The x-axis of the graph shows frequency. You can change the frequency range with the frequency dropdown, for example, to 6 GHz. The x-axis will update to show a range up to 6 GHz. To inspect the response in more detail, hover the mouse over the frequency axis and use the scroll wheel to zoom in. You can also click and drag to pan left and right across the frequency range. To return to the full view, right-click on the x-axis and choose Reset Zoom. The same interaction works on the y-axis, which shows attenuation or gain. Hold the mouse button down on the y-axis to move the scale up and down, or use the scroll wheel to zoom in around a particular level. Now let's add real hardware to the calibration model. Under Antenna, you can select from a list of predefined Aronia antennas, each with its measured frequency response. For example, choose the OmniLog Pro 1060 antenna. The graph now shows the frequency response of this antenna from 150 MHz up to 6 GHz. You can see that this antenna has a predominantly negative gain, with dips down to roughly -12 dBi in some regions. To improve overall sensitivity, you can add a preamplifier. Open the amplifier dropdown and select the UBBV 1060 BPA amplifier with amp.on. This adds additional curves to the plot. The blue curve shows the amplifier gain, which is around 20 dB at lower frequencies and falls to about 15 dB at higher frequencies. The white curve shows the total RF path, combining the antenna and amplifier responses. Here, the overall gain can approach 25 dB in some bands, while at a dip, the combined gain may be closer to 7 dB. You can also include cables in your RF path. Open the cable dropdown and select, for example, a 3-meter RG316U cable with SMA to SMB connectors. Because this cable is defined up to 10 GHz, the frequency axis may automatically extend to 10 GHz and show a roll-off at higher frequencies. As expected, the additional cable slightly reduces the overall gain, which is reflected in the white RF path curve. Above 6 GHz, antenna and amplifier data may no longer be available, so the RF path is interpolated largely based on the cable performance up to 10 GHz. If you only care about operation up to 6 GHz, right-click on the x-axis, choose Set Zoom, enter 6 GHz as the end frequency, and confirm. The scale will return to a 6 GHz upper limit. You may also use other antennas that already include an integrated preamplifier. For example, select the Hyperlog 4060X antenna, which operates from 0.4 to 6 GHz. In this case, you will see a strong gain of roughly 40 dB across the operating band, even without adding a separate amplifier. If you are measuring near a very powerful transmitter and want to protect the system, you can add an attenuator. Under Attenuator, choose a 10 dB model. A green line appears in the plot with a flat response, indicating 10 dB attenuation across the defined range. This shifts the RF path curve downward by 10 dB, reducing the system sensitivity accordingly. Because this attenuator is also specified up to 10 GHz, the x-axis may again expand to that frequency, and you can adjust the zoom as needed. In some measurements, you might use a near-field probe instead of an antenna. From the probe menu, select a probe such as the PBS1H1 up to 6 GHz. The graph shows a gain of around 40 dB for the probe, combined with any cable you have selected. If you zoom in at 5 GHz, you can see that the white RF path curve is about 1 dB below the probe's gain, reflecting the small loss of the short cable. You are not limited to predefined components. If you have your own antennas or amplifiers, you can define custom attenuation or gain profiles directly in the GUI. There is a separate video that covers creating these custom curves in more detail. For example, you might create a test_antenna entry that represents a device from 500 MHz to 4 GHz with a gain of around 40 dB. This lets you accurately model the performance of your specific setup together with a chosen cable length. Changing the cable length automatically changes the RF path attenuation and gives you a realistic overall system response. You can also apply a similar power offset. If you want to add a fixed dB gain to the system, you can use the power offset slider or enter a value directly. An orange line appears at plus 6 dB, and the RF path will shift accordingly. This is useful when you need to account for known fixed gains or losses in the path. These are the main elements in the calibration section. If you also have GPS position information available, you can enable it here and attach the location data to the calibration block. To return to the block graph editor, click the green pencil icon in the top toolbar. You can see how the ribbon bar and calibration blocks are connected to the rest of the mission. If you like, you can toggle the ribbon bar from the View menu to adjust how much space it uses. This concludes the video on adding and configuring a calibration block in a mission. For more information, check out our other videos on our YouTube page or visit erroniausa.com.